Hey gang, welcome back for another video here on JoChem. Alright, so in this video, we get to kind of usher in a new wave of awesome chemistry. In this video, we're going to talk about ester enolates, why they exist, what they can do for us, and we're going to kind of usher in a new reaction with ester enolates called the Claisen Condensation. Okay, so if this is your first introduction to ester enolates, I'm hope that this word right here, well actually both words, are familiar, right? You know what an ester is. We know that you need a carbon chain a little bit and a carbonyl right next to an oxygen and then a continuation of some type of carbon chain, right? That's what defines an ester. It's almost like smushing a ketone and an ether together, all right? And we've definitely discussed enolates, right? We know an enolate, on some level, is a structure that exhibits both, we have the carbon-carbon double bond and the negative charge up top, but can also be drawn like so. Okay, so what happens when we kind of fuse these two things that we know together? Well, something pretty cool. So, let me just erase this. Let's do a quick kind of look at ester enolates and how we generate them, which luckily is no different than how we would generate any other type of enolate. So let's just take a simple ester like this one right here, okay? So in the presence of base, let's even use something right here. What you'll typically see, especially when we dig into the Claisen condensation, is that we use kind of whatever is the ester-ish type, the ether-ish type of character in our ester. So in this case, this would kind of be ethanol. So you would typically see, you put in a mixture of ethanol and then you have its deprotonated form, ethanoate. Here we go. So if we have this, what we're absolutely going to do is we have two available protons in that alpha position. Our base would go ahead and deprotonate, electrons swing over, and then they kick up onto oxygen, and you generate your ester enolate. So no different than what we've done time and time again. However, the cool part about ester enolates is that you don't have to worry about whether you're going to generate a kinetic enolate or a thermodynamic enolate, right? Because the fact that we have this kind of ether-like character means we can basically work with, we only have one alpha carbon to work with to deprotonate. So a lot of predictability with ester enolates, which is why they're so popular to use as nucleophiles, particularly in the Claisen condensation. Okay, so let's dig into the Claisen condensation. So let's do an example, and then I want to talk about some requirements and things, little, not tricks I would say, but I guess characteristics of the Claisen condensation. So I'm going to bring back that same ester I had, and actually very, very similar conditions. I'm going to have ethanol and then that ethanoate right here, and then a second step of acidic workup. So you could just have, a lot of people generically write H plus and H2O. Don't be shook if you were to see something like H2SO4. You just want something that's going to bring H plus to the table and not participate in the reaction. So I'm going to even just go ahead and erase this and just leave the more generic H plus H2O. Okay, so gang, the very first step, as we just kind of saw, was we're going to generate an ester enolate. Okay, so in this scenario, we don't really have anything that we're given to attack. So we have plenty of this ester, and that's exactly what we're going to work with. So not only is it going to be used as to kind of generate, to transform into our nucleophile, but it's going to be our electrophile, right? Because there's still a carbonyl here. There's still something that a negatively charged species would be attracted to. So There's an oxygen in there. So just like you would attack with any other enolate electrons slowing down, we reform a double bond. The alpha carbon, remember, that's where these electrons are coming from. They are going to go all the way over here and attack the carbonyl carbon, and then electrons kick up onto oxygen. So we're going to have a little bit of a hot mess over here. So what do we get? I kind of like to draw this part first, and then because we are bonded over here, so hopefully you follow this. I'm going to dot this carbon, which is where I bonded from. Dot there. Didn't touch this part of my ester over there. And I'm going to draw this methyl group down. Then over here, right, I make a bond, and that's this carbon right there. Whoop. No longer is that that's an O minus. And then I have an ethyl group. And I'm going to draw the O, like the ether-ish part up here. Okay? Because what's going to happen, like we saw in we just generated a tetrahedral intermediate. So what's going to happen is that intermediate's going to collapse. And the best leaving group we have, right, basically, could we just eject what we added? Yes, absolutely we could. But that's not, there's no point to that, right? What we can do is we can eject this right here. This O, this ethanol derivative right here. And now you can see kind of why we've chosen this acid bit, or this alcohol pairing. Is because that is what we're eventually ejecting off into solution. We already have it, right? So I've reformed my carbonyl up here. I do no longer have this part of the molecule. So we've eliminated one kind of ether-esque part of our ester that we have now kind of stitched together. And what you can see is we have generated this right here. And one requirement of a Claisen condensation is, at this point in the reaction, this was not the best choice of leaving group. We need some kind of energetic payoff for picking and ejecting a leaving group that wasn't spectacular. And it's at this point that you need to quench this base, right? This base needs to be quenched. You can do that by protonating it, and the most acidic proton in the molecule will be the one caught in between our new dicarbonyl species. So when you do a Claisen, this last step is mandatory. You have to have a proton on this carbon that lies in between your two carbonyls. If there is no proton there, the Claisen condensation will not happen. So because we do have a proton here, you can just dump the electrons onto that carbon. So that occurs, now we have condensed something, right? Now we understand why it's called a condensation, right? And while we do have a negative charge there, we do have a second step of workup. I'm going to just draw hydronium. But that is how the Claisen condensation proceeds. And I'm going to go and loop over this and add a little bit more clarity, because I did forget to mention something. Okay. So, a Claisen condensation occurs when you have an ester enolate. So you need to start with an ester, and then you need base, like a basic solution, and the base present should match the ether part of your ester. So if this is O methyl, you better have methanol and methoxide, right? Here we have, a 2 carbon piece, so we have ethanol and ethoxide, right? Definitely misspoke earlier in the video. Ethoxide and ethanol, my bad. So you generate your ester enolate, which we'd previously done, so I just went ahead and drew it. But you do that by deprotonating this alpha carbon position. And what's important to know is many of these steps, I'm drawing straight arrows. The better way would be that these are reversible steps. Reversible until you get to this part. This is the part that energetically seals the deal. This is the irreversible step. Once you've done the condensation and this mandatory depronation step, you continue to move forward. That is why if you don't have a proton present at the middle carbon position, your Claisen condensation is a no-go, because there's no kind of forcing the equilibrium forward step. You would just kind of get to this part and then unravel backwards. Okay? So in this part, we did have a symmetrical Claisen condensation. It wasn't mixed. I want to do one more example, kind of just illustrating this, and then we will absolutely do a mixed Claisen example. So let me erase this, and we'll do another one. Okay, gang, so let's run through another Claisen condensation example, and this will also be a symmetrical one, not a mixed Claisen. Okay, so if you can see up here, I'm given an ester, our first step of, a mixture of methanol and methoxide and acidic workup. So because we see that we do have an ester here and the means to do it, we will make an ester enolate. So that would happen by methoxide performing an alpha deprotonation. I'm going to kind of start with the mechanism back down here. Going to run through this a little bit faster than the previous one. So we do formulate the ester enolate right here. Okay. So because they don't give us, this problem doesn't present us with another carbonyl to attack, we just use another ester. Sometimes the trick of these problems is just drawing everything the most efficiently. I'm going to go ahead and draw this. Okay, so electrons swing down. These bonds from the carbonyl, or the alpha carbon, find the carbonyl carbon on the other molecule, and we attack. So I'm going to go ahead and redraw this and then kind of fill in where I need. So I reform my carbonyl. I have my dot carbon right here, and I like to basically take the group that came off the alpha carbon I attacked for and flip it down. So I'm going to go ahead and draw this little branch with the cyclopentane ring down here. And now I can actually draw the bond from this alpha carbon to this new carbonyl carbon over here. So I have an O minus, and I'm going to keep this O methyl up here in this part of my, I missed the carbon right here. So honestly, a lot of it is the bookkeeping and spatially drawing things so you don't lose your mind. Okay, and remember, these arrows are reversible. Nothing irreversible has happened yet. Sometimes I just out of habit do that, and that's not a great habit, so I'm sorry about that. So at this point, we have generated our tetrahedral intermediate, and we're going to collapse that sucker. Electrons swing down, and remember, it's not the best leaving group we have available, but it's the one we're stuck with. We're going to kick off the ether part of our ester here. It just happens to be methoxide. Again, also an reversible step. So I didn't do anything over to this part of the molecule. Reform my carbonyl. All right, we got this right here. And remember, it's at this point you can check, will my Claisen go to completion? Will the condensation go all the way to the end? And we do have our methoxide, newly kicked off methoxide right here. The answer is yes, because the carbon alpha to both of our dicarbonyls right here does indeed have a proton, which is available to be picked off. The electrons, oh boy, go right back on that carbon. Sorry, not beautifully drawn. That is the irreversible step. And At this point, we can then bring in our acidic workup. Whoop, I'm going to draw this over here. And we get our product, which is, whoop, sorry, a lot of drawing. I kind of wanted to do an example of something that would end up being a little clunky. Okay, cool. Okay, gang. So now we've done 2 symmetrical Claisens, full mechanism the whole way. I want to show you 2 more problems. One where the Claisen condensation doesn't go because of a lack of proton at that position, the carbon in the middle of our 2, our dicarbonyls, and a mixed Claisen. So I know this video is getting a little bit on the longer side. If you're still with me, I appreciate you. I'm going to clean this up, and then we will do the failed Claisen and then a mixed Claisen. Okay, gang, so let's look at that unfortunate scenario where someone may be trying to pull a fast one on you and give you a situation that looks like a Claisen, but does not have the requirements to go to the full product of a Claisen condensation. Okay, so in this reaction right here, it looks very similar to the first example we looked at, right? We have an ester, we can see right here, we have kind of 2 carbons in our ether section of our ester, and we see that's, we have ethanol and sodium ethoxide, as well as acidic workup. Sounds like the perfect recipe for a Claisen, but that is for us to find out if it is or not. So, I'm gonna kind of run through this. I'm not gonna do the full-blown mechanism, but remember, so we have, at this position, we do have an H. So we can do alpha deprotonation, and we can generate this ester enolate. We will then bring in another unaltered ester, and we'll do some attack. We form the tetrahedral intermediate. Of course, I said I wasn't going to do the full mechanism, but here I am. And again, if I accidentally forget to do this, just remember it's not irreversible until we have that proton, the deprotonation step. Okay, tetrahedral intermediate collapses, we kick off our not so great leaving group. And it's at this point, gang, where remember, we need to evaluate, can we quench the base that we produce, the not so great leaving group, and push the equilibrium, and to a final product, and actually get some type of definitive thing that will not go backwards? The answer here is no, because we don't have a proton here for this base to pick off. We only had 1 H on this alpha carbon to start, and we had to use it to generate the ester enolate in the first step. So you can quickly kind of evaluate a Claisen condensation if the carbon you're working with, it has to have 2 protons, right? One to become an ester enolate, and if it's doing the one doing the attacking, it also needs to provide the proton for the base you kick off in an acid-base reaction to then push to a final product. So, no Claisen condensation because there's no proton available for the base we generated. Okay? So, I think you'll get decent at identifying this. So anything kind of tertiary that you're working with is kind of a no-go. But if you had something like this, like we did in our first example, I think you could see 2 H's, right? One for the enolate formation, and then this is for quenching that base. Okay, cool. So let's erase this, and then I want to show you a mixed Claisen, and then we'll call it a video. Okay, gang, last but not least, let's round out this video with a mixed Claisen condensation. Okay, so enter in this problem. So we actually are given 2 esters that are not the same, and you can see that we do have in their both of their ether sections of their ester, we see that we have a 2 carbon type deal, which makes no surprise that we see ethanol and ethoxide as a first step as far as what we're going to use and what environment we're in to generate our ester enolate. So the first thing we need to think about is, since we have two non-symmetrical, two non-identical esters, which one will be the ester enolate? So remember, this is a proton game as far as who has the ability to become an enolate. So if we look at this structure, you can see clearly at this position, we have two H's available, and even as a, advanced foresight, we can see that if this is the enolate we go with, the ester enolate we go with, we have enough protons to become an enolate, as well as satisfy that criterion of a Claisen condensation and quench the base will kick off at the end. And now we take a look at here. This ester, luckily, you can see, obviously we have no alpha carbon on this side of our carbonyl, and while we do have a carbon here, there's no H available for us, there's no proton to deprotonate. So by default, this will be our ester enolate, the ester on the right. Okay, so if we were to generate that ester, it would look something like this. If we were to then attack, we'd have this type of electron flow. So again, I'll do some arrows like that, some arrows like this. So this is, again, just stay organized. I know it's very spaghetti monster-esque, right? There's lots of, organic limbs flying everywhere. Just stay calm and just play the game of who is attached to whom. Okay? So I had this alpha carbon. Oh, no, we're not bonding there. We're bonding here. Sorry about that. So let me go ahead and just draw what was my ester enolate. And I know I have this carbon is now bonded to this carbon. And I know I have an O minus. So kind of drawing things upside down now a little bit. Okay, cool. So I know I have my benzene ring as well as my ethoxide piece right there. Okay, so remember, tetrahedral intermediate collapses. We kick off our not so amazing leaving group. We form the carbonyl. We have a dicarbonyl now. Cool. Remember, we generated this base and we need to quench it. We need to take care of it. Luckily, we do have a proton at the position in the alpha carbon between our dicarbonyl. Do a quick little proton change. Dump the electrons on that alpha carbon. Remember, this is now our irreversible step. Seal the deal. Got the energetic boost. Ooh, sorry, I'm getting a little sloppy. Just a lone pair. Whoop, I'm gonna actually draw it over here. And that's why we have some acidic workup to take us on home, push us across the finish line. Hydronium always there to pick us up. So, final product. Don't know if this is gonna fit. Let's give it a try. Yep. And there you have it, ladies and germs. Okay, so I know this video was a bit on the longer side, but think about everything we just covered. We talked about how we can use esters to generate ester enolates. Something, enolates, something we've worked with in the past. Now we've kind of, tossed in a different functional group, and we saw that basically sets us up to use one alpha carbon. So then we talked about the Claisen condensation, how we can attack, not only use esters to be, generate a nucleophile, but then how to also use the same species as our electrophile and to attack and to generate a tetrahedral intermediate, which we've covered before. collapsing the tetrahedral intermediate and ejecting a leaving group that's not spectacular, and then learning about the requirement of the Claisen condensation to have the extra proton, to give it the energetic boost, the payoff, to push it to completion. And we saw that whether it was, a HOMO type situation where we had the same ester do both the nucleophile and the electrophile's job, or right here, a mixed situation where we had, and typically in these mixed, you'll get a scenario where only one could be the ester enolate. There's only one that can have the alpha carbon generate the enolate. So, gang, a little long video. Luckily, there's another reaction in this chapter called the Claisen condensation. It's basically the same as this. It's just one that causes a cyclic product. The chemistry to come is very cool, so strap in, let's have a good time, and I'll see you in the next video.